Now let's look at arc length in parametric form. So we say that if we have a curve C and it's defined parametrically by x equal f of t and y equal g of t, where t is between a and b, and f prime and g prime are continuous and not simultaneously zero between a and b, and c doesn't intersect itself on the interval from a to b except possibly at the endpoints, then the arc length over that interval is going to be the integral from a to b of the square root of f prime of t squared plus g prime of t squared dt, or dx dt squared plus dy dt squared. If you remember from section 7.4, arc length back there, and remember I used the letter L for arc length, was equal to the integral from a to b of the square root of 1 plus derivative quantity squared in either dy or dx depending on what variable the function was in. Well, now arc length is just going to equal the integral from a to b of the square root of x prime squared plus y prime squared. So let's find the arc length of the curve on the given interval. In order to do this, I need to find x prime and square it and y prime and square it. Let's start with x prime. So if x is equal to 6t squared, x prime is going to be 12t. If I take x prime and I square it, 12t quantity squared is going to be 144t squared. This is y. Y prime here would be 6t squared. If I take y prime and I square it, 6t squared quantity squared is going to be 36t to the fourth. Therefore, the arc length, L here, is going to be equal to the integral from 1 to 4 of the square root of 144t squared plus 36t to the fourth dt. Now recall that the square root of a squared plus b squared will never ever equal a plus b, neither will the square root of a squared minus b squared equal a minus b. So you cannot distribute the square root over addition and subtraction. It's not possible. In order to solve this, what we're going to have to do is factor, and then we can distribute the square root over multiplication. If I look at the two terms that are underneath the radical, what do they have in common? Well, they both are divisible by 36 and t squared. So I'm going to factor out a 36t squared. If I do that, I would be left with 4 plus t squared. Now that I have multiplication, I am allowed to distribute the radical over multiplication. So this becomes the square root of 36t squared times the square root of 4 plus t squared dt. Now if we clean this up, we know that it would equal, well, the square root of 36 is 6, and the square root of t squared, on the interval from 1 to 4, the square root of t squared would end up being a positive t because your limits of integration are positive. So that would be 36t and then times the square root of 4 plus t squared dt. Now this becomes a u substitution problem. What would u equal? U would equal what's underneath your radical. In this case, u is equal to 4 plus t squared. The derivative du would equal 2t dt. Well, you don't have a 2t dt, you have a 6t dt. So if you multiply both sides by 3 du is going to equal your 6t dt. Therefore, this becomes the integral from t equal 1 to t equal 4 of, instead of the square root, I'm going to write the 1/2 power. That 4 plus t squared is your u, and the 6t dt is your 3 du. Now if we integrate this, I add 1, that becomes to the 3/2 power, and then divide by that number, but since it's a fraction, I'm going to multiply by the reciprocal, and that gets evaluated from t equal 1 to t equal 4. Moving over here to the right-hand side, my arc length is going to equal, well, notice those 3's cancel, and that's just going to be 2 times whatever u was. Remember, u is your 4 plus t squared. That gets raised to the 3/2 power, and this gets evaluated from 1 to 4. Let's plug in our limits of integration. If I plug in a 4, I'd have 4 plus 4 squared. So 4 plus 16 is going to be 20, so it's going to be 20 to the 3 halves. Minus, if I plug in a 1, this is going to be 4 plus 1 squared, or 4 plus 1, which is 5, to the 3 halves. Now you can enter your answer in like this in WebAssign, or what you can do is simplify it. Let me show you how to simplify it. The square root of 20 to the 3 halves is really just the square root of 20 times the square root of 20 times the square root of 20, because it's the square root cubed. Let's clean that up. Well, the square root of 20 times the square root of 20 is just 20, but we can actually simplify the square root of 20. That's actually the square root of 4 times the square root of 5. So this becomes 20 times the square root of 4 times the square root of 5, which becomes 40 square roots of 5. The square root of 5 to the 3 halves is just the square root of 5 times the square root of 5 times the square root of 5, which is 5 square roots of 5. So now we have 40 square roots of 5 minus 5 square roots of 5, and that's 35 square roots of 5. And if I multiply 2 to that, the arc length here is 70 square roots of 5. So you can enter your answer like this into WebAssign, or you can enter your answer like this top one right here. Let's look at the last thing in this section, area of the surface of revolution. In section 7.4, we learned that surface area was equal to 2 pi times the integral from A to B of the radius times the arc length, because it was the square root of 1 plus derivative squared. So it was radius times the arc length, and either dy or dx depending on the variable that was given. Well, it's no different here with parametric equations. So if we have a parametric equation that's given by a smooth curve where x is equal to f of t and y is equal to g of t, and that smooth curve does not cross itself on the interval from A to B, then the surface area of revolution formed by revolving this curve around one of the coordinate axes is given as follows. Your surface area is going to equal 2 pi times the integral from A to B of g of t, well, g of t is your y here, times the square root of dx dt squared plus dy dt squared dt. Well, that piece is just your arc length. So it's still your radius times your arc length. Well, here that happens if you're revolving it around the x-axis. And if you think about it, if you have some kind of curve and you're revolving it around the x-axis, the distance there for that radius is equal to a y movement, which is why the radius here is your g of t. The other formula is the formula for rotating about the y-axis, and that's again very similar. S is equal to 2 pi times the integral from A to B of, in this case, f of t, which is what your x is, and this again is just your arc length. So it's just radius times arc length. And here again we are rotating this about the y-axis. So if you have some curve and you're rotating it about your y-axis, well, the radius, the distance from that to the curve, this guy right here is an x movement, which is why your radius here is f of t. So surface area is still 2 pi times the integral from A to B of radius times arc length. And the radius is still going to be perpendicular to the axis of rotation, so you just have to figure out which one of these are you looking at. Is your radius supposed to be x? If it's x, it's going to be whatever your function is that x is equal to. If your radius is supposed to be y, then it's going to be whatever your function that y is equal to is. Let's look at the last example where we're finding the area of the surface generated by revolving the curve about each given axis. Let's remember that we're doing this times the arc length. So it's always times that arc length. Since it's times the arc length, we're going to need to figure out what is x prime, what is x prime squared, what is y prime, and what is y prime squared. We will go ahead and start with that. If this is x, x prime is equal to 1, and x prime squared is just equal to 1. If this is y, then y prime is equal to -2, and y prime squared is equal to +4. Therefore, we know that that arc length piece is going to equal the square root of 1 plus 4, which in this case is just going to be the square root of 5. So let's figure out what the surface area is going to end up being, because we're looking for surface area for A, x-axis, and then B, y-axis. For part A, we're rotating this about the x-axis. Remember, surface area is always going to equal 2 pi times the integral from A to B of the radius times the arc length. Well, I know that my arc length here is the square root of 5. That part's done. I just need to figure out what's the radius. Well, it's the x-axis. So remember, if you have some function and you're rotating it about the x-axis, the radius is still going to be perpendicular to the axis of rotation. This distance here is a y movement. Therefore, in this case, my radius has to equal what y is, and that is 4 minus 2t. So I know that my surface area here is equal to 2 pi times the integral from 0 to 2 of my radius, which is my 4 minus 2t, times my arc length, which was a constant here, it's just the square root of 5, and then dt. Well, just like we said, the square root of 5 is a constant. Let's go ahead and pull that out of the integral, and that becomes 2 square roots of 5 pi. And then if we go ahead and integrate this, the integral of 4 is 4t. The integral of negative 2t is negative t squared, and this gets evaluated from 0 to 2. Plugging in those limits of integration, we end up with 8 minus 4, and then minus a bunch of zeros. Therefore, in the end, this is going to be 4 times 2 square roots of 5, or 8 square roots of 5 pi. Therefore, the area of the surface we get by revolving this parametric equation about the x-axis from 0 to 2 is 8 root 5 pi. What about the y-axis, part B? Again, surface area is always going to be 2 pi times the integral from A to B of radius times your arc length. Well, the arc length has not changed. That guy is still going to be the square root of 5, so I just need to figure out what the radius is. Well, this is the y-axis, so if you have some curve and you're rotating it about y, this distance that you're traveling right here, that's an x movement. So in this case, your radius is equal to t, because x of t is equal to t. Putting it into our formula, surface area is going to equal 2 pi times the integral. Those limits of integration are still from 0 to 2. The radius in this case, again, is just t. Your arc length was the square root of 5, and then dt. Square root of 5 is still a constant multiplier. Let's pull that out of the integral. So we have 2 square roots of 5 pi, and then if I integrate t, I get t squared over 2, and then that gets evaluated from 0 to 2. Well, notice I have a 2 here and a 2 here, so those are just going to cancel. And it's really just then the square root of 5 pi times t squared evaluated from 0 to 2. Plugging in those limits of integration, I'd have 4 minus 0. Therefore, the area of the surface here is 4 square roots of 5 pi. That's it for parametric equations in calculus.